And I was talking to the organizers and lecturers, and we think it's a good idea to switch in the program and have the Q&A session after the last lecture, okay? And then I think it works better. So starting tomorrow, the Q&A will be after, so Laura will start tomorrow at 2, and then we have the Q&A, and then we finish. Okay, so it's a real pleasure to have with us for this week Professor Laura Reina. So Laura did her PhD at CISA in Italy, and then after a short postdoc in Brookhaven, she got a professorship position at the University of Florida.
No, Florida State University.
Oh, sorry, Florida State University in Gainesville.
Yes, the Seminoles against
Yes,
the Gators.
I know. So
just
I'm not much into
me neither, but I learned it in 25 years. I learned it.
Yes, and she's a professor, at Florida State University in Gainesville, and she's an expert in collider physics. She organized a very important effort in the U.S. called the SNOWMAS for future colliders, etc. Mm-hmm. So I'm sure you're going to have a great set of lectures from Laura. So thank you, Laura.
Thank you, Rogerio. So it's a real pleasure to be here and to have the possibility of talking about collider physics. But first of all, I was thinking while I was coming here, and that this is kind of special to me because, as Rogerio has mentioned, I was a student at CISA. In the very early, not probably the super early days, but quite soon in the history of the school, there was internationally called ISAS, the International School for Advanced Studies, which is attached to the ICTP in Trieste. And I was thinking that the very first school I went to was an ICTP school, right? Because I was there, right? It was real, very, very natural for me to do that. So it's kind of special to be here and be part of this event again because I had great memories of that school as of anything else that I did during my PhD time. So it's great that now Sao Paulo has this institute and is expanding the effort and educating our community to grow even stronger. So this was my memory thing. And then a big disclaimer right just off the bat, which is collider physics is broad, right? And to start with, it has, of course, a huge experimental component and an equally big, I would say, if not equally huge, theoretical component. And I'm a theorist. So I will not be here teaching about the nitty-gritty of detectors or anything like that. So I know the little that I need in order to make meaningful theoretical predictions. And meaningful means to the required level of accuracy that we need to have a meaningful comparison with data, with the experiment. But if you ask me why they picked that component as opposed to that other component, I may not know the answer, right? And I'd be more than happy to investigate that with you, but I may not know it off the top of my mind or have maybe never seen it because we are two separate, specialized community at the same time. Those two communities, they come together, however, in the phenomenology of colliders. And this joint venture is extremely important, right? And it takes some effort on both sides. It takes the effort for experimentalists to figure out what are the really important things that theorists should know in order to come up with meaningful predictions. And it takes from the theoretical side the interest and the effort to understand if your theoretical prediction doesn't match at all what is actually measured at colliders. And this is an ongoing process that has to be updated as we go along, and as experiments in particular become more and more precise. And this is because depending on what you need to compare to, you can, and we are used to this in physics, to kind of look at the structure of things, at the bare bone of things, and then start dressing up the bare bones with whatever we need in order to understand more and more of the specifics. So when we needed a comparison with experiments at the level of 50%, that's a back of the envelope calculation. But when you need a comparison at the level of 20%, that's not a back of the envelope calculation anymore. You need to start bringing in, still you approximate things when it's reasonable. As you will see, by the time we look at the physics that the current collider, the LHC, will be able to deliver by the time it runs at high luminosity, so the high luminosity LHC, we expect precisions in some of the measurements, in a lot of the measurement, at the percent level. And at that point, it's really revisiting what you have done so far, not only pushing what you already used to do, but also revisiting things that you have assumed so far that are not justified anymore, and will easily bring in some percent error here and there on the theoretical side. So there is where the dialogue becomes really important. It becomes a dialogue with the experiments that does not require you to know each single technical details, but it requires you to know what is measured, and for you to be able to compare to that. And one of the goals that I will have in these lectures is just first we need to start, it's great that we have a very diverse community here, people who know probably more than me about experiments, and people who are working on cosmology, right? Some very different things. So we'll have to start setting some common ground and some language and some ideas. But then we will go through what is the reality of colliders these days, and what it takes on the theory side to be able to compare to the data that are coming from colliders. And I would like at the end to maybe work out with you a couple of cases in which we can really dissect everything that goes into the measurement, everything that goes into the theoretical prediction, and see how we talk to each other and what has been done and what will have to do in order to match the precision of the high luminosity LHC and the precision that means both in measurement of properties of the particles that we know and in discovering things that we do not know at future colliders. So because it is a very broad topic, of course there are already available to you a lot of references that you can go and read and you can go and listen to, because there are a lot of video-taped lectures of previous schools that you can look. And schools like this one are great resources. We have other big series of lectures that normally contain a lot of information and very interesting lectures for you, like in the US, for instance, you have TASI, the TASI Summer School Institute, and one of the traditions is to write, to have a write-up of the lectures that you give, that not always we do, but we try. So you'll find online, and I have a collection of references for you that I will send to be posted on the website for you to look both at the general introductions to collider physics and specific topics in collider physics, which is also what I would like to do with you. So to come by the end to look at specific topics and specific examples, physics sector by physics sector. There are also books, and books are good references, but I think the lectures are the best for you because they are very much in touch with the current reality of things, and it's a fast evolving field, so a field that it's hard to condense and to crystallize in a book, right? A book can have the basics, which are also important, but it will not be up to date with what is being done these days at the LHC, or what is the ongoing discussion for future colliders. So coming then to the topic of these lectures. So collider physics, in a way, so let's start setting the framework. What I would like to do with you today is just introduce some important concepts that allow us to identify different kinds of machines, different kinds of collider machines, and understand the physics that you can do at these different kinds of machines and why they're done the way they're done. And also look at what we have had in the past that has brought us till today, to what we know today, and then have a look, dedicate some time to what we have right now, which is the Large Hadron Colliders, and look at the close future, which is its upgrade to high luminosity, and then look at the future in terms of these fundamental parameters that describe the physics of these machines. So we will not go in any detail. We will try to get the big picture of what the field has looked like, what the field has given us so far, and what the field promises to give us in the future. Of course, so in a way, you can sort of think of today as why collider physics? So why do we have collider physics? It's a justification of the past and of the future, right? At the same time. So if you think it through, almost anything we know nowadays about subatomic physics came one way or the other from colliders. It is not an overstatement if you stretch a little bit the definition of a collider, right? So not every colliders have been as powerful as the one that we have today. They had much lower energies. Sometimes they started with fixed started collider, not two beams collider against each other. They made, it depends what you interpret. I mean, even scattering processes in general are sort of collisions, right? So, but even without going to the prehistory of our time, but just staying into the last century and the current century, everything really we know about fundamental particles, elementary particles, and their interaction has come from colliders. The standard model that you have heard today about, they started hearing today about, was proven and discovered at colliders. And the properties of all the other particles have been studied at colliders till the very end, till the discovery of the Higgs, which is probably the first beyond the standard model thing that we have in our hands, even if it belongs, strictly speaking, to the structure of the standard model. But as we will discuss towards the end of this lecture, there is a lot to it that is not understood. So the idea is simple. So the idea is, for all modern colliders, is to take two beams of particles. They can be elementary or not, right? And to just accelerate them, energize them as much as you can in such a way to then collide them and use that energy in very inelastic processes to produce anything that can fit into that energy momentum budget in general, right? And that is a way to both probe things that are not that massive or that don't need that much energy, but to probe them in different energy regimes. And so it allows you, for instance, to study how certain interactions behave at low energy, at higher energy, at even higher energy, and see if your understanding of the behavior of those interactions is consistent with what nature tells you. It also allows you to cross the threshold of higher and higher energy and therefore look into more and more massive physics. So this is what has allowed us to discover very massive particles of the standard model, like the top quark or like the Higgs boson, right? So it's just going up in energy, right? So how you do that is, so one of the fundamental, if you want, parameters that identify a collider is the energy that is available to produce the final state that will allow you to investigate new physics or properties of particles that you already know. So that is the first, you will not see any complicated physics today, but just to set the standard. So if you have, you consider two beams of particles that are, that are moving one against the other. The idea of a collider is very simple. It's just to have a head-on collision among those. So if you take a particle from the first beam and a particle from the second beam, the first one will have, you can write its momentum, its form momentum, as some energy. And then since they're coming along the same direction, I can take that direction as the z-axis, for instance, of my frame. And so I will have a 0 component for the x and the y components of the momentum, and I will have some momentum p1 in the z direction. And then I would have the momentum of the second particles in the second beam that will come with this kind of momentum. And in general, you can just write these in a compact form as E1, P1, specifying, having in mind that structure, and E2, P2. Now, if you go to what we call the center of momentum frame, this is the frame in which P1 plus P2, 3 momentum, is equal to 0, right? And in that frame, so what we call the center of momentum energy, which is P1 plus P2 square, is just E1 plus E2 square. Now, this is a condition that in general is verified not only in the center of momentum frame, but is verified even in the lab frame when P1 is equal to minus P2. So this condition here is also verified in the lab frame when P1 is equal to minus P2, which is precisely the condition in which you are accelerating one beam against the other, right? Now, that allows you, this is a nice, and it's an important, so this is an important point. It is an important point because this object, S, is an invariant. And so identifying, being able to define the properties of the machine in terms of this object does not depend then anymore on the frame that you are using. And as a matter of fact, it corresponds, if you realize this condition, also to the momentum that you measure in the center of mass in the lab frame. So colliders often are defined by the square root of S. So they're center of mass energy or center of momentum energy. And this square root of S can be estimated in general, in particular if you have 2 equal particle beams, so 2 beams of particles that are the same, so in terms of such that also their masses, M1 and M2 are the same. This is really what you define to be the energy in the center of mass, and you can see that is equal to, at that point, to twice E1 or twice E2. So that you can say it's equal to twice the energy of the beams, so the energy of the particles in the beams. So colliders will be defined by this square root of S, or S, depending if you want to give it as an energy or an energy square. Now, the remark that I made here is pretty important, and it's important because this is not a condition that is verified by all colliders. In particular, it's verified by colliders in which the beams are made of elementary particles. But if the beams are not made of elementary particles, the constituents of whatever you are colliding may not verify the condition P1 equal to minus P2. So if you take, for instance, and here is the first distinction that we are going to make between different kinds of colliders. If you take colliders, the beams of which are made of particles that are elementary, like lepton colliders, so for instance, E plus, E minus colliders, those particles are elementary, so that condition can be very strictly verified at the level of the constituents of the beam. So lepton colliders that so far has been one and the same thing as E plus E minus collider, but you can think them as L plus L minus collider more in general, because as you may have heard, these days we are talking both about future E plus E minus collider, and I know that my L's are very similar to my E's, but let me see, this is the L plus L minus, so lepton colliders. But you may have heard that these days we are also talking about a future machine that is called a muon collider, in which you collide mu plus and mu minus particles among themselves. So the same is true in that case. The energy in the center of mass is the same, both in the center of momentum and in the lab frame. And the particles are coming in with equal momenta in both frames, right? Equal and opposite momenta in both frames. When you go to hadron colliders, this is not true anymore, because even if the initial hadrons, and here we are talking about colliders that can be proton-antiproton or proton-proton colliders. This is what we have had so far and what we're talking about for the future as well, right? So when you have the proton now, the antiproton, as you know, they're not elementary particles. And so what really you collide are the constituents. So you collide the quarks, antiquarks, and gluons. And even if the P and the P bar, or the P and the P in the two beams start out having equal and opposite momenta, the constituents will have a fraction of that momenta, which is distributed with a given probability, and not necessarily the probability, the fractional momenta carried by constituent of one is equal and opposite to the fractional momentum carried by the constituent of the other. So in general, the events in the lab frame would be boosted. So in the center of mass, you can still define the square root of S, but the event in the lab frame, you have to remember when you calculate, when you do your calculation, to boost the momenta, because there will be a longitudinal boost in the discussion. And when we get to discuss hadronic colliders and hadronic processes, we will look more in details to this point, right? So machine, we have identified, therefore, however, these parameters, so the E center of mass, which, as I said, is an invariant, that is a good parameter to specify the nature and the kind, so that if you want, the reach of a machine, right? What you will have to remember, however, is just that because of these, when you specify a given center of mass energy, a given ECM, or a given square root of S for a lepton collider, you have all that energy available, because it's the same that you have in the lab frame. So when you specify that energy for a hadron collider, you'll have available only a fraction of it, because the constituents will not carry the full thing, but it will carry only a fraction. So energy-wise, the reach of a lepton collider is face value what is given to you. For a hadron colliders, you will always have to rescale. So if we have the LHC that has a center of mass energy of 13 TeV, we cannot probe a particle up to 13 TeV, because extremely rarely in the center of mass, both constituents will come in with almost the entire energy of the corresponding protons. Most of the time is about 1/10 of that energy, or a little bit more, 1/7 of that energy, or a little bit more. You can look at the distribution of the different probability of the two partons, and you will see that it's peaked more or less around. There will be events that have the full thing, but they're extremely rare, right? So this is something to keep in mind, that therefore, hadron colliders, if they want to have the same reach of lepton colliders, they have to have higher energies. That's clear, right? Now, of course, the kind of physics that they can probe is also slightly different. Not extremely different, but slightly different. Because in one case, you are colliding leptons, so objects that do not have strong interactions. In the other case, you are colliding quarks and gluons, or hadrons, that have strong interactions at all levels. They have strong interactions both in the perturbative and non-perturbative regimes. So a much more complicated situation, at the same time also a much richer situation, in which you can learn a lot of things about strong interactions firsthand. If you look at the half-full glass, if you look at the half-empty glass, you scratch your head and you say, how do I get rid or take care of the non-perturbative parts that I don't control so nicely as I do control the perturbative part. So we see both aspects of the problem in our discussion. So now, so this is first in blue that we have here, the first parameter in which we will attach to different kind of machines. When we see a list of them, both in the past, now, and in the future, all of them will have a square root of S attached to them, which will give us, if you keep in the back of your mind what we just said, it will give us some idea of which kind of physics we can do, right? Now, one remark that you may want, so since we are looking at this discussion, and I said initially that when collider physics started, a lot of the experiments were fixed target experiments. So there were experiments in which you would throw a beam of particle at a fixed target. Well, if you go through the same exercise, you can see that energy-wise, this is a more advantageous kind of situation. So in the other case, you will have clearly to do to work out, if you want to work out the energy that you have available, you will have to start with a situation in which the momentum of the second object, this object here, is 0, because it's a fixed target. Right? And so when you calculate your square root of S, so when you calculate your S quantity, so for a fixed target, when you calculate your S is given just by the same formula that you have here. But so you will have let's write it first in terms of momenta. And we have the P1 square, the P2 square, and the 2P1 dot P2, right? Now, this is the mass of the object in the first bin square. This is the mass of the object in the second bin square. Probably they're equal, it doesn't matter. But then here you will have the 2 multiplies E1, E2, and you don't have the P1 dot P2 part because the P2 is 0, right, in this case. So let's say I chose arbitrarily that the 2 is the fixed target, so the P2 momentum is 0, right? So, and here in E2 itself, so E2 will be the square root of the M square plus P square, and P square is 0 because it's P2, and so this is M2, right? So at the end of the day, I haven't said it, probably this is something that I should have said from the very beginning. Of course, these are, in collider, we accelerate particle to the more than relativistic, what we call the ultra-relativistic regime, so with the velocity very, very close to the velocity of light. And so the energy of the particles, not the fixed target, but the other one, as the 2 energies that we had considered here in the both moving beams, are much larger than the mass of the objects. So in this sum here, we can rightly approximate this expression to just 2E1, which is the energy of the moving beam, times the mass of the second one. What I'm saying is just that M1 square and M2 square can be neglected in first approximation. The E1 is much bigger. And so you see that the square root of S in this case is the square root of 2E1 M2. And for the very same reason that M2 is much smaller than E2, you see that this situation here is much more convenient. So it's much more allows you to reach higher energies. So this is just a parenthesis in this initial discussion in which we want to get a little bit of sensitivity or sensibility, if you want, to what a machine really can do, right? Now, as you may have encountered, as you may have encountered in different situations, in different occasions, you know that there are circular collider and linear colliders. And typically, plus and minus colliders, so lepton collider are both linear and circular, but PP collider in general, all we know, they're circular colliders, right? That's what we have ever built. So why for the plus and minus machine we have both options? So clearly a circular collider is advantageous from the point of view of what I said at the very beginning, energizing your particles. So why? Well, because you keep going. So how do you energize them? How do you accelerate them and make them faster and faster, gain more and more kinetic energies just through a very clever combination of electric and magnetic fields. So this is an entire class in electrodynamics applied to collider physics, right? Very, very clever. It goes from basic principle, very simple one, to very sophisticated one. Yes? Because P2 is 0. Yeah, it's in the fixed target case. Yes, so my 2 is the target, which is fixed. This is another, so I'm discussing now the fixed target case, right? Okay, so what I was saying is just that for the case of the way we make in a circular, so the way in which you make particles acquire more and more energy is by accelerating them through a series of electric and magnetic fields that are used in colliders, right? So now, if you can iterate the process as you do in a circular collider, clearly is advantageous, right? The other possibility is not to iterate the process, to have just it in one shot, but at that point, you have to stretch the length of your apparatus, right? And that is the case of linear colliders, right? So why would you go to a linear collider instead of a circular collider? Because something is taking energy out of your beam in the case of a circular collider. And what is taking energy out of your beam in the case of a circular collider is what we call synchrotron radiation, right? Now, if you look at what synchrotron radiation, what it depends on, so the radiation that is emitted because the particles are accelerated due to the curvature of their trajectory. So changing the direction is an acceleration, and synchrotron radiation is the emission of radiation due to the acceleration of particles that you can calculate in elementary electrodynamics, right? So if you look at how much energy you lose, so if you want your delta E, where delta E is the energy of the particles in the beam, roughly speaking, leaving aside other factors, this is proportional to the inverse of the radius of the curvature of your trajectory, and is proportional to the fourth power of the energy divided the fourth power of the mass of the particles in the beam. So it goes more or less like this. So what that tells you, if this is large when m is small, and this is small when r is large, right? So that means that if this m is the mass of an electron, or this m is the mass of the proton, since there is a difference of 3 orders of magnitudes between one and the other, there is a big difference in delta E. So what that means is just that electron colliders have a serious problem in getting to, unless you build something that has a really large radius that compensate for that. So they tend to radiate a lot, right? That's the problem. So in order to, if you want, and if they radiate a lot, it's difficult to get to higher energies. So if you wanted to reach higher energies, at some point you have to switch to a linear collider for an E plus E minus machine. Things that you don't need to do when you have a PP machine, so when you have a hadron colliders, because this mass is much larger. And so if you keep a larger enough radius, you have a delta E that is acceptable. So a delta E for which, even if there is a synchrotron radiation, the synchrotron is not killing the beam. So it's not killing the energy that you accumulate in the center of mass. So this is what makes the difference for lepton colliders. So for what I call L plus L minus collider, it's really the discriminant between a circular and linear. So that's why you will see machines that are linear and circular for E plus E minus colliders, but you will not see them for a PP collider or PP bar colliders, okay? So this is another aspect of the problem, so another thing that you wanted to take into account. Now, and take these as a sort of parenthesis in our discussion that is mainly aiming at figuring out what else do we need in order to identify the properties of a machine. So we say this is an important thing. This is a sort of remark that we needed to take into account. Another important thing is the introduction of the concept of luminosity of a machine. And this comes in, well, probably before doing that, or right after doing that. So let's introduce the concept of luminosity first. So this is the other important thing that we wanted to define in such a way that then we can look at the different kinds of machines that we have had and we have and will have and see how they, two parameters define all of them. So the concept of luminosity comes in because here we have said, well, we have defined what is the energy in the center of mass available for a given process to happen. Then the next step will be, of course, with that energy, we can now, knowing the energy that we have available, we can calculate a given process with two particles in the initial state colliding against each other and producing a given final state, and attach to that process the probability for that process to happen, which is proportional to what we in particle physics call the cross-section for a given process. So to connect, first of all, to this discussion, given the center of mass or given S in general, so either square or not, we can calculate the probability for a given scattering process that I can identify in general with two particles in the initial state producing a given final state. So A and B are, let's say, in beam 1 and beam 2, and they interact and produce a given final state X. How do I calculate that? So what I calculate first is not the direct probability for a given scattering process, but I calculate the probability amplitude for that scattering process. So using quantum mechanics, and in particular, the glorified version of quantum mechanics that we call quantum field theory, you calculate that you have most likely all of you studied in your classes, you calculate one of which is the standard model that you have been introduced to this morning and will be introduced during the next 4 days of these lectures. So you take as your quantum field theory the standard model. You take as your quantum field theory another theory beyond the standard model that you may want to work with, and I've heard that some of you work in different extension of the standard model. And you calculate the scattering amplitude for AB going into X. And then you calculate from here the probability amplitude. You integrate the amplitude, let's say, over the phase space of the final state. And I'm going very hand-waving here. And you get what we call the cross-section for that process, right? So you have a very well-defined pattern to get the cross-section of that process. Now, how do you get the number of events of that kind that you really have produced in your machine, right? So for that, you have to think that the two beams that you collide are not a continuum distribution of particles. Particles come in bunches. In the different bunches that are colliding, so particles are coming in bunches. So let's say one in one direction and one in the other direction. Bunches have a density of particles in them. So the one, for instance, has a number, let's say the one of type A, the bunches contain Na particles. The one of type B contain Mb particles. And so they have a certain cross area that we will call A. And they have a frequency. So they come in space in time as f. 1 over a given number of seconds, so the frequency. So the bunches are spaced in time between them as 1 over f, which is a given number of seconds t, right? So what that means is just that the number of events per unit area of the beam and unit time will be proportional to the frequency f, the number of events of type A in one beam, the number of events of type B in the other beam, and divided by the cross area of the beam. And the proportionality factor here is the cross section, right? So the proportionality, so I can write an equal sign here, saying that the proportionality factor here is what we calculate as the cross section. And this is the part that depends on your S parameter. So it's the part that depends on the characterization of the collider that we have had there. This is very simplified. If you look at some of the references that I will quote in the bibliography, you see a couple of good reviews of collider physics from the experimental point of view, and you will see that sometimes things are not defined univocally, they have a distribution, and et cetera, et cetera. But in first approximation, this is what the main idea of how to obtain the number of events that you are producing per unit area and per unit time. And this object here, or maybe I can use a different color, this quantity here is what you call the instantaneous luminosity L, right? So this is one of the two different luminosity instantaneous luminosity, L, that you can then integrate over a given period of time and get what we call the integrated luminosity. And the integrated luminosity is given in different ways. So when you then integrate the instantaneous luminosity over time, for over a given period of time, this period of time can be the life of a collider, if the running of the collider is over, is done, or it can be the amount of time the collider has run up to there, right, up to that point. So for the case of the LHC, this delta T will be from the beginning till now, and for the case of colliders that are done and gone will be the entire time during which the collider has run. Of course, it doesn't run continuously. Of course, life is not so easy, right? So there are different corrections to this formula. For instance, if I really wanted to get the rate of events produced, so the events produced per unit per unit time. So I will have also to take into account some efficiency of the detector, and depending on what the events are. So, for instance, if we are looking at how many Higgs events, to say one of the things that experiments are measuring the most these days, so how many Higgs events are produced at the LHC or have been produced at the LHC, I have to specify, there is a thing to say how many Higgs events have been produced. It's a different thing to say how many Higgs events have been produced in a given channel. Because at that point, you have to look at the specific decay of the Higgs, and then you have to multiply, not only, you don't calculate only the cross-section, you calculate also the decay probability in that specific channel, so you multiply by branching ratio and so on and so forth. And so at this point, it's a good point to talk about units. So how do we measure these things into? So from the formulas that we have here, right, so clearly you see that the number of events per unit area and unit time have a cross-section as a proportionality factor that multiplies the luminosity. So the cross-section, clearly, this is a pure number, right? So the number of events. So the cross-section has to have the same units as the area that we have here. So the cross-section, therefore, if we use if we work in natural units, so if we use C equal to H equal to 1, then the dimension of a cross-section, which is a length square, is an energy to the minus 2. So the dimension of the cross-section, for instance, in our calculation can be in inverse powers of EV or powers of EV. And if we wanted to look at the physics of the LHC, it's convenient to get multiple of the EV. So we can, for instance, define the unit in GeV to the minus 2, right? So these are the units of our cross-section in general, right? So units of energy to the minus 2. Now, cross-section in general are measured in, however, given in bizarre units. So this is just a straight consequence of the fact that this object has a unit of a length of square that is equivalent to an energy to the minus 2. This is just that, right? But cross-section traditionally are measured in units that are called barns or multiple of barns that are connected to more understandable units like units of length or units of energy by a conversion factor. So one barn is 10 to the minus 24 centimeters square, right? So if you want meter square, you do the convention, the conversion, right? So now I leave it to you using these. So using the fact that you are working in natural units, to also transform these to a given number of GeV to the minus 2. There is a conversion, yes?
Sorry for a trivial question, but on the left-hand side, I see number of events per area per time. So on the right-hand side, it should have units of 1 over 2
Sorry.
On the left-hand side of the equation,
Yes.
1 over area, 1 over time. So I would think on the right-hand side, I should have 1 over area, 1 over time.
Yeah, it's F is 1 over time.
But the cross-section cancels the area, so I don't see 1 over area.
Per unit time, yes, yes, sure. Yeah, so without the sigma, this was right, but with the sigma, it's just per unit time. Yeah, thank you. So the conversion factor that you see there is, if you calculate it, I get something of the order 2500, so it's 2568 or something like that. So this is of the order of 2568, and you can calculate it. Or vice versa, you can convert GeV into barn, right? And so that will tell you the 1 GeV to the minus 2, which is the unit on the other side, is of the order of, what I get is 3.8 in 10 to the minus 4. Yes, on 2 to the minus 4 barn. So you can convert it the other side and say that 1 GeV to the minus 2 is approximately of the order of 3.8 in 10 to the 4 barn. And with these, you can go and measure and give all the cross-sections that of any process at the LHC. And of course, you will see that often you need powers of these units that are not higher powers of this unit, but they are lower powers of this unit. So a lot of the LHC cross-section are given in terms of nanobars, they're given in terms of picobars, they're given in terms of femtobars. So these are also the units with which you give your instantaneous luminosity and integrated luminosity. So if a collider is giving you a luminosity of a given number, this luminosity, the integrated luminosity, is the luminosity that is given just in powers of areas, right? So inverse areas. So if you are given a luminosity of a given number of inverse barns or a submultiple of barns, and you know the cross-section of a given process in the same unit, you can get the number of events, right? So this is the trade. This is just the use that you do of these characteristic of a collider, which is the luminosity. So these other, apart from the cross-section, apart from the center of mass energy, the definition of these other parameter, which is either the instantaneous or integrated luminosity. So in a way, this name comes very much from the power you have in a given machine to explore rarer and rarer event. So the more luminosity you have, the more you can hope to see processes that have a smaller probability. Now, with these two elements in our mind, so with two main parameters, we can now look at the evolution of different colliders over time. So we have seen a very broad description of the kinds of colliders that we can have. We have seen a description of what identifies them. So what have we had so far, and what are we having right now, right? And why this is related to some particular kind of physics that we can do, and where do we want to go from now on? So before getting to the present, which is the LHC, let's look at what have been the most important colliders that have allowed us, as I said at the very beginning, to know everything we know in subatomic physics so far, in particular to probe the Standard Model to a level of precision that has so far confirmed the Standard Model as the theory of elementary particles at the electroweak scale, so up to the electroweak scale. Although we know from first principles and from a lot of experimental information that is coming, experimental evidence, if you want, that is coming mainly from astrophysical and cosmological measurement, we know that clearly the Standard Model cannot explain problems as big as dark matter, dark energy, baryon, anti-baryon asymmetry of the universe, and so on and so forth. But for what concern elementary particle in interaction at the electroweak scale, the standard model has so far been tested at an incredible level of precision. Where is that knowledge come to us? Where has come to us from? So if we wanted to review some of the most important colliders of the past, there will be many, but I think that some important ones, some fundamental ones, have been starting from the 80s, have been an E plus E minus collider that was called the LEP. This collider had, so it's way before your time. So this collider had two main runs. They were called LEP1 and LEP2. And what made the difference between the two was the center of mass energy. So here we will list the center of mass energies of the colliders that we are going to discuss. So right, I will list it here. So the first one, LEP1, was really tuned to be at the peak, at the resonance of the Z boson. So two previous hadron colliders, UA1 and UA2, at CERN had discovered the W and the Z. And that was the famous confirmation, if you want, of the gauge symmetry of the standard model. So those were the gauge boson predicted by the standard model in the presence of a Higgs mechanism, massive with masses of the kind that the model predicted. And as you have seen, or you will see in one of your lectures, the masses of these particles are dictated by, are proportional to both a parameter that comes from the scalar sector of the theory and the gauge coupling. So a very constrained model that would predict a relation among them that was experimentally verified. So the standard model was sort of confirmed as a theory. And so what people did was to really tune the machine at the resonance of the Z boson to have an incredible statistics, as we will discuss. This is what happens when you tune something at the resonance, and study the properties of this particle, right? So the energy was for around 90 GeV. For precisely, it was 91.2 GeV, right? And then LEP2 went up in energy to start probing also some other processes, like production of pairs of Ws, of W bosons and other processes that are slightly higher energy. It got almost to the point to even see the Higgs boson before it was shut down. And so the energy were increased between a little bit before that, like 130 and 200 GeV. So this was the energy, the more or less, I think it was 210 or 209 GeV. That's what I can find, remember. So the luminosity that was accumulated in this collider, and here, because they're past, we can look at the integrated luminosity, so everything that was accumulated over time. So we will look at L, although we can also indicate in parentheses that the instantaneous luminosity that was typical of the machine. So the instantaneous luminosity was typical of the order of 10 to the 31, 10 to the 32, centimeter to the -2, second to the -1. But the integrated luminosity that we can quote here in picobarn to the -1 is the unit that, and well, I haven't, I could have put probably the GeV up here to make it more symmetric. So for these machines, was of the order of, in one case, in the case of LEP, I think it was of the order of 200. In the case of LEP2, was the order of 600 inverse picobarn, right? So this is as much inverse picobarn, right? So it means that if you want to calculate now how many events of a given kind were accumulated for a given process in those machines, you take the cross sections of those process and you multiply by the luminosity of the machine and you get the number of events. Now what that means is just that if you have a process that is very, very rare, that has cross-section below the picobarn, maybe of the order of a femtobarns, you will not have events enough in the machine to measure anything. So the more the luminosity, so the larger the luminosity is in terms of inverse powers of barn, the more you can see in your collider. That's the idea of luminosity. So when luminosity, integrated luminosity, we get to the order of inverse femtobarns, you will be able to see processes with cross-section at the level of the femtobarns. Where the luminosity becomes of the order of inverse, the next inverse power, which is attobarns, you will be able to see cross-section, processes with cross-section of the order of the attobarns. So rarer and rarer processes. That's the idea of this quantity. And of course, I haven't said that, but this machine was at CERN. And at the time, and probably I can also give you some idea of some idea of the years during which it ran. And so for LEP, this was between 89 and 95, LEP 1, and for LEP 2 was between 98 and about 2000, right? That's my memory. So let me just see if I'm not giving you anything wrong. No, that was right. So this was between more or less 89 and 95, and this was between 96 and 2000. And you remember the experiments because probably you have looked at them. So what the name of the experiment are typically the name of the detectors. And you remember that, or you have heard talking about detectors with the name of Aleph, Delphi, L3, and Opal. Now, more or less at the same time, there was another experiment, this one in the US at SLAC, that was called SLC, stand for Linear Collider. That was linear. So LEP was a circular machine with a circumference of about 26 point something kilometers, 27 kilometers. Circumference. And SLD, on the other hand, SLC, sorry, on the other hand, was a linear collider. Always an E plus E minus machine, but this time linear. And this was a SLAC. And it had only one phase. It had a center of mass energy just centered at the Z, center of mass energy, so the 91.2 GeV. It had an integrated luminosity much lower of about 20 inverse femtobarn, even picobarn, sorry. It ran more or less at the same time, so between 18, they started at the same time, but it ran up to 98. And the detector was called SLD. That's what I was saying before, right? Bad alignment. 91.2, 20, 1989, 98, and SLD. And then we had others, in particular where there was a collider that ran at DAISY that is called HERA, and was one of a kind that I haven't mentioned so far, because it was an E plus minus P machine, right? So it was an electron-proton collider, so not lepton-lepton or hadron-hadron, something that I haven't mentioned in my introduction, but that has been realized over the years, right? It was particularly important. We will see a lot of measurement of that when we'll discuss one of the elements that go into evaluation of hadronic cross-section, which are the famous Parton distribution functions. A lot of the measurement of Parton distribution functions to these days came from HERA and stay as some of the best measurements. So this machine ran at a center of mass energy of 320 GeV and had a luminosity of about 500 inverse picobarn. These are just numbers for you to complete your, to have the full picture. It ran between 92 and 2007, I think, yes. And you may have heard about the detectors because they are attached often to these PDF plots that you see that were called Zeus and H1, right? And this was at DAISY, as I say, in Germany. And finally, we got to a PP machine, actually a PP bar machine, so a Hadron Collider. There was the Tevatron. At Fermilab in the US that had two main iterations, two main runs at two different center of mass energy, 1.8 TeV and 1.96 TeV. Right? So the center of mass energy much higher than the one that we have here. And integrated luminosity that reached, again, higher levels. So during the two runs that were called run 1 and run 2, as you see, not only had you see these, if we go back to our previous discussion, you see now how the center of mass energy of these Hadron Collider are much higher than the center of mass energies that were used at LEP. The reason is both the fact that LEP was tuned to be at the resonance of the Z, but also because the effective center of mass energy that you have available here is not the full center of mass energy that you see, right? So that doesn't mean that we can have available this much energy in the center of mass for produce something. Still, remember that the Tevatron had energy enough to discover in 95 and 96 at the top, right? At the top quark was discovered at the Tevatron. And as we see, the integrated luminosity, as soon as we quote it, we see that it's much larger. So the integrated luminosity for run 1 was 160 inverse femtobarn, and for run 2 was of the order of 10 to the 4. Right, so this integrated luminosity here was 170 in inverse pentabar, and for run 2 was about 10 to the 4 inverse femtobar. That means 10 inverse picobar. That means 10 inverse femtobars. So what that means is just with so I circle these in yellow because it pertains to the luminosity. I circle these in blue because it pertains to our discussion of the other parameter, the center of mass energy. So this is our L, if you want, right? And this is the center of mass energy, the two parameters that we discussed in the introduction to this lecture, because they really parameterize a collider. And when you compare the two between the prototype plus and minus machine and the corresponding, if you want, not exactly corresponding, but the Hadron Collider that was operating more or less, not exactly at the same time, but more or less at the same time. Actually, there had a lot of overlap there because run 1 was between 1987 and 1996, and run 2 followed between 2001 and 2011. And here you remember the names probably more recent, in more recent times of the two detectors. There was CDF and D0. When you see the comparison between two kind of colliders, an E plus E minus collider and a P-bar collider, so a hadron-hadron collider that ran more or less during the same time, you really see the kind of features that I told you before. So the fact that the center of mass energies are higher, still not everything available to do physics, and then the luminosity typically of a hadron machine are higher, and they've reached. So thanks to this. So what kind of physics did they do before we switch to the recent times? So what was available to us at the time when the collider that we have this day, which is the LHC, came online? It was the whole physics that was developed by LEP, by SLC, by Hera, and by the Tevatron. And so LEP, as I said, studied the standard model, and in particular studied the physics of the Z, the physics of the W, in great details. So when you look at the what are called precision fits of the standard model, most of those plots that fitted together, that compare precision measurement of masses and couplings more or less, of the standard models between the theoretical prediction and experimental measurements, they still use measurement from lab 1 and lab 2. And SLC. Then with time, the measurement coming from the tevatron became important. And in particular, what became important of the tevatron was the measurement of two most important things, that is the mass of the W boson and the mass of the top quark, because the top was discovered at the tevatron. Right? So from the tevatron, we got the measurement of the mass of the W and the measurement of the mass of the top. Still no Higgs, because the Higgs hadn't been discovered at that time. So really, the full structure of the standard model, the testing and stress testing of the correctness of the model itself came from a huge series of measurements that were developed in the 80s and 90s and the beginning of the year 2000 through this set of machines. And mainly through the measurement lab and the measurement at the tevatron, complemented by the knowledge, the more in-depth knowledge of pattern distribution functions that came through measurement of deep inelastic scattering at the Hera collider, so it's an EP machine. So this was the past. So this was the pre-LHC Hera. And then the LHC came online. And for that, I can keep writing things at the blackboard, but I think it's probably more convenient, if you want, to look at one of the plots that the LHC has prepared for us. And for these, let me switch on one slide that I prepared for you. And I think I should just do these, right? So we see it up there, right? So when you look at, so the title says the message. So the LHC is really exploring the TeV scale, right? So let's look at what we have here. So first of all, you see the years of operations of the machine, right? So on the scale, there is a time scale, and the time scale goes of more or less between 2010 and the future. And the future goes up till the 2040s, right there. So there is a lot in front of us. Sorry? Ah, okay, sorry. It's this one, right? Ah, yes. Now I see. Thank you. So, okay. So you see that the timeline that goes more or less between 2010 and 2040s. So a lot of time in front of us. So on this timeline, you see the operation of the machine, right? So the machine started with what was called run 1, then moved to run 2. Run 2 was completed. We are now in run 3. And what is in front of us, what here is called the run 4 and 5, is what is commonly defined as the high luminosity LHC, right? So let's read what this plot tells us. Well, first of all, you see the evolution. The machine has on times and off times. So these LS are the long shutdowns of the machine, where upgrades of the machine happens on the experimental side to bring up either the energy, as you see in going from run 1 to run 2, a little bit also in going to run 3, or the luminosity, because here the energy will go up, but also the luminosity of the machine will pick up a factor of kind of 5-ish between before and after. So indicated on the same plot, so you see the energy phases, as I said. It started at 7 TeV in the center of mass, then went to 8 TeV, and then 13 TeV, and now operating at almost 14 TeV, 13.6 TeV. So the final goal is 14 TeV. These are PP colliders, so 7 TeV per beam, or the half of whatever number you see there per beam. Now, if you look at the numbers down here, the 30 inverse femtobars, 119 inverse femtobars, 450 inverse femtobars, and then 3,000 or 4,000 inverse femtobars, this is the expected or accumulated already integrated luminosity. So what that means is just that during run 1, the machine accumulated the 30 inverse femtobars, By the end of run 2, 190 inverse femtobars. And then we expect by the end of run 3 to have at least 500 inverse femtobars. And by the end of the high luminosity LHC, a factor of, if you look at that, is a factor of 20 almost with respect to the end of run 2, which is what even now during run 3 we are using for all the measurements that have been delivered by the LHC. So if you look at all the papers that have come out from the LHC so far, they are all run 2 papers. So they're all based on run 2 data. The analysis of run 3 has started, of course, but is ongoing, so we don't have that. And if we look at the performance of the machine during that time, it's way past what was expected originally. So the machine has outperformed definitely itself and has already given us something very important. And of course, we all see, yes, I know what it is, it's the Higgs, right? But yes, it's not, well, first of all, let me emphasize one more time. This is not a little thing. So we got used to that. I say, okay, the LHC has discovered the Higgs, no big deal, right? No, it is a big deal because as we will see in one of the illustrations that I have for you later on, it's not obvious at all. And it's incredible that the Higgs was discovered exactly where it was predicted by the standard model for the consistency of the model. That I'm not saying that the standard model explains what it is, but that the standard model is so constraining to really, by the end of the story, have singled out a little tiny corner of the parameter space where the Higgs has to lie in order to be consistent with everything else that we know of the standard model, not only at the tree level, but including the full quantum structure of the standard model, so radiative corrections, correlations between the different parameters of the model, and so on and so forth. So this is a really big deal that came, unfortunately, or fortunately, right away, so that now we are bored that nothing else has come anymore, because it came immediately after the LHC switched on, right? So, but the interesting thing, the very important thing that the LHC has also done during run 2, so after the discovery of the Higgs, was the measurement of the properties of the Higgs. So right now, most of the couplings of the Higgs to gauge bosons and fermions are known at the level of 10-15% from the LHC. And the high luminosity LHC projections, officially, they go to a few percent for many of them. But as we know, they were based on projection for run 2. They were pessimistic with respect to what the run 2 of the LHC has really delivered. So we do expect a high luminosity LHC to really have a serious Higgs precision program in place by the end of, we expect a better measurement already by the end of run 2, but definitely by the end of the LHC to have reached a really impressive Higgs precision program. Now, the only thing that probably will not be measured in its full glory will be the self-coupling of the Higgs, so the interaction of the Higgs with itself that is important for the measurement of the potential of the Higgs, as you will hear during your standard model lectures. But definitely what we think is just that by the end of the high luminosity LHC, the measurement will be probably at the level of a 50% is predicted right now, probably better because of the reasons that I just said. Now, this machine is also a unique machine, has also delivered in an incredible number of precision measurement. It will deliver an incredible number of precision measurement during the high luminosity LHC for top physics. Top physics is really important because top, as you know, is the heaviest of all quarks. And one of the things that we really do not understand in the standard model is the hierarchy of fermion masses. So why the masses of quarks are so different one from the other. And so the one that has the highest coupling to the Higgs, which is also a very mysterious part of the standard model, and it's probably, there is nothing certain in our understanding of nature, but one intuition is just that probably something that can give us good hints of physics beyond the standard model. So measuring deviations in these couplings or in the behavior of top quarks is really important. And with this respect, because the top is so heavy, and you need to produce at least one, most likely two, most likely together with something else, you need a lot of energy in the center of mass to do top physics. So even a future machine like an E plus E minus collider, unless it has energy above 500 GeV, will not be able to do good top physics, where good means better than the LHC, better than the high luminosity LHC. So you really have to go to machines that we will illustrate as future colliders. So hadron colliders with very high energy in the center of mass, so 10 times the LHC, or for which you have a huge statistics of top produced, and then statistics helps you. Or machines that are in the more hypothetical world, like this new machine that is being studied, which is a lepton collider that collides muon instead of electrons, that can reach higher energies and has the advantages of a lepton collider. So it's, as we know, has cleaner events from the point of view that there is no much strong interaction in the initial state. So, so it has the potential of seeing more. So we are very hopeful, because if you look at where we are here in 2024, and look at how many years of running of the LHC we have in front of us, and look at the kind of statistics that is coming in by the end of the high luminosity LHC, is a factor of 20, as I was saying, compared to what we have accumulated so far, and on which we are basing our projections. So the reach of the percentile level precision is really an option. Now, another thing that I wanted to show to you and comment about is the fact that I should use these. Doesn't want to move ahead. Do I have to point it in some particular direction, or is it? Ah, okay. Thank you. Okay, so it was easier than I thought. So one of the things that we also have to appreciate about collider physics, which is important to bring it up from the very beginning, is just that collider physics is very broad. So it's not just one measurement. There are tons of measurements. And the more your machine can deliver, the more measurements you can have. So what I mean is just that if you take the LHC and the high luminosity LHC, but even the LHC starting in run 2, it has statistics enough not only to measure total cross-sections, but to measure, for instance, differential cross-sections. And that is a huge difference. It's a huge difference because total cross-section can be dominated by certain region of the characteristics of the events, so what we call the phase space of the events, so their energy momenta, transverse momenta, angular distribution, and et cetera, that have the bulk of the cross-section, but not the new physics. And the new physics maybe is concentrated in regions of the differential distributions of different processes that are less populated, but more important because they're more sensitive to new physics. So the possibility of having statistics and precision enough, accuracy enough at the level of the experiment to measure differential distributions is very important. And in this picture that is kind of propaganda picture for the LHC, but at the same time has a lot of content. You can see at during the different phases of the machine, from 7 to 8 to 13 to 13.6, so going from run 1 to run 3, where we are right now, so this is limited probably to run 2 in this illustration. You can see the different measurement from 221 to 222 to 223 processes, more and more diverse and with the larger multiplicity processes. And you can see how the errors on the simpler, if you want, processes experimentally are, for some of them, really tiny. And the gray bands that you see here are the theoretical prediction, which in some cases already cannot compete with some of the experimental measurements. So a lot of theoretical work is needed and is being done and has been done in order to compare with the precision of the machine. So it gives you, in a way, the idea of the power of this measurement and the power of these machines in covering a broad range of phenomena. Not to talk about that are kind of illustrated in this zoomed plot in which you see the comparison between theory and experiments for some of the 2-to-1 and the 2-to-2 processes, it's pretty impressive, right? The kind of comparison that we can have. These are still total cross-sections. They're not differential cross-sections, so it's the total. And then I'm going to add a little bit of a comment about the importance of differential cross-section. On the right-hand side, on the other hand, I'm just collecting for you, and I do not pretend you to read all these, but if you then look back at the slides and you zoom in, you will see that these different sectors of this plot represent searches for different kind of particles belonging to different standard model, beyond the standard model theories, for which the LHC has been able to put bounds on the masses of these particles. And you can say, yes, they haven't discovered them. They put bounds on the masses of these particles. But this is nevertheless very important. It's very important to know what is there and what is not there, because you move on. You move on to something else, right? And the LHC has been able to do all these. So this is just to emphasize how collider physics is extremely broad. And even if with collider physics, both direct searches and precision measurement collider physics, you cannot really explore extremely high energies because directly you can explore up to the energy of the machine. And indirectly, sometimes you cannot reach, you cannot exclude a physics that at a mass that is as high as what can be done in a single experiment at lower energy sometimes. So experiment like the G-2, for instance, can exclude specific models more than the LHC does. But it's one measurement. And even if you see deviations there, you can have hypotheses about what that can come from. It can be extremely important to have that measurement. But whatever hypothesis you have will have to be consistent with everything else that you can measure in a controlled environment, which is the environment of a collider, where you can tune things to go and look for what you are looking for. The moment you have an idea, the same is true for searches of other physics beyond the standard model, dark matter, for instance. Clearly, colliders are not a dark matter experiment. They can search for dark matter, but they are not comparable to other dark matter experiments, to the myriad of dark matter experiments that we have distributed in a lot of astrophysics searches. But the moment you have an idea or you have a hint of something, that particle that is a dark matter particle does not come alone. It will have to come in the context of a theory that justifies it, a theory that has a lot of other consequences. It has to have its fellows around it. And that will have to be consistent with everything that is coming from a machine like the LHC or the high luminosity LHC or a future collider. This is not to say that it's better or worse. It's just to say that it's a really powerful tool that you have in your hands in order to explore things that you do not know. So, since you are going to get closer to the end of my lectures, I wanted, first of all, one thing that I wanted to emphasize with just a simple drawing is why it is important to be able to measure distributions, right? And why that is important, why the LHC has given us this incredible opportunity. So I wanted to illustrate that with a very simple picture, right? So if you consider some distribution, right? So you're here, here you will have your number of events distributed over some, let's say, energy or momentum. Transverse momentum is a typical variable that you will see we use at colliders because, as I was alluding to at the beginning, we don't have much control on the longitudinal energy, but we know that the transverse momentum is 0 to start with, so you have much more control on the transverse momentum. But this is a parenthesis. And assume that this distribution goes normally, we'll discuss this shape, it has a shape of this kind, right? So most of the cross-section, if you measure the total cross-section is the area under the curve, right? So if you measure the total cross-section, it's dominated by this region. And of course, when you go and look at the theoretical precision for this distribution, there will be effects due to quantum effects, higher order effects that are beyond what you can calculate in the simple tree-level approximation that are distributed both in the low PT or low energy and in the high PT and high energy. So typically higher order effects will maybe change a little bit the shape here. They will enhance it maybe a little bit here. But they may also change the shape of the cross-section over here in both directions. So I'm just saying that the shape will be changed by your theoretical prediction. Why is it important to be able to compare with experimental measurement? Is because if you compare the total cross-section and the new physics is over here, you will not see it. Because this is a region that statistically in the total doesn't matter much, unless here you have a spike, a huge resonance over there, right? But otherwise, you won't see it at the level of the total cross-section. But if you are able to predict the shape of this distribution accurately, and if you are able to measure it accurately, so if you have statistics enough to get into this region, maybe here you are in a region, so you're going toward higher masses, maybe there is something here. If there is something here, if there is another resonance here, so if there is a new particle that is leaving maybe at a mass that is out here, or maybe even farther away from whatever in this region, you will see the distribution picking up at some point. So the shape of the distribution in this case will be different in this region, will be a shape that at some point will have to rise to give, I'm exaggerating it, but it will have to rise to give origin to our dream that there is another particle out there, right? And so if you are able to measure this region, so the high tails of distribution, and I give this example because it's easy to understand the fact that there is a particle at a high mass, but the deviations can be on other distributions as well. They can be angular distributions, and the points of distribution typically have, depending also on the symmetry properties of the new theory that you're bringing in. So because of that, measuring distributions is really important, and the LHC is giving us this possibility. So this is the region, so the low energy region is typically the region in which you measure the parameters of your theory because you have a lot of statistics there. So here is the region in which you get to measure more precisely parameters like the masses, the couplings of your theory. You measure them down here. Here are really regions where you spot new physics, where you can see the effects of new physics directly, right? So, or the presence of new physics, because if you think in terms of also of an effective theory interactions, effective interactions are typically proportional to energy over the scale of new physics. And so it's when you go to high energy that these effects become larger. So that is where mainly you will see them. So when we think to the future of the LHC, as well as when we think to new colliders, so colliders that will come after the LHC, we have mainly two ideas in mind for which to push that these machines will have to realize. Either they will give us more precision, or they will give us more energy. Those are the two. So if they give us more energy, clearly you can keep doing the work of the LHC and of the high luminosity LHC, pushing the energy to the boundaries. If they're going to give us more precision, we can do the job of really comparing between theory and experiments at a higher level, and therefore constrain theories beyond the standard model with precision. So I think we will have time to discuss this tomorrow, but I wanted to leave you with this idea. So if you think of the big fields of BSM theories as being somehow identified with some mass scale, which is the mass scale of the particles that we haven't discovered yet, that are the typical mass scale of the new particles that belong to this theory. So if you think them in terms of a mass scale, and some coupling to standard model particles, so they will have couplings among themselves, or they will have couplings to standard model particles. So coupling to standard model particles. And if you imagine that the LHC has explored some of these ranges, so you can plot the mass scale of new physics versus the coupling between new physics and the standard model, right? The LHC will explore quite a bit of this phase space. But it's limited. It's limited in mass reach, and it's limited in the sensitivity it has to the couplings when the couplings becomes weak, when the couplings become small. So if you imagine that the LHC has explored a certain area here, let's say this one, which is the LHC, ideally, you would have to both explore weaker couplings for a given mass range or extend the mass range in this direction and all the gamma of possibility in between, right? So one thing that you want to do is just to extend the reach of the LHC to weaker couplings or couplings that have been hidden in the background of the LHC so far. And we also maybe wanted to extend, what you want to do is also to extend the energy reach of the LHC to higher energies, so to here. And this is precisely what we will see is being proposed for two different classes of future colliders that we call colliders that expand the energy, or multi-TeV colliders. That therefore go to energies that are above the center of mass energy of the LHC quite substantially, right? And not just 1 TeV more, but a lot more, right? And the others are machines that can explore weaker and weaker coupling, become more and more precise, and therefore precision is also something that allows you to identify new physics that is in touch with the standard model by small deviations to standard model parameters. And those, because most of our, if you want, still unknowns are in the Higgs sector of the standard model, both for the Higgs coupled to itself, for the Higgs coupled to gauge boson, for the Higgs coupled to fermions, we call these machines Higgs factories. And they will, of course, a Higgs factory is not just a precision machine. And so something that will discover new physics through indirect evidence of new physics because of deviations from masses and coupling of the standard model, as well as a multi-TeV collider is not just a discovery machine. So something that will see new physics through direct evidence of new physics, producing it. So there will be both. But let's say that the main characteristics of these machines will be to push the energy or to push the precision. And so to have evidence of new physics because of direct production, or evidence of new physics because of precise measurement of couplings and masses of standard model particles, including the Higgs. So none of these machines, as the LHC, even multi-TeV collider, will be precision machine. And Higgs factory, maybe they can discover something because they will be different from the LHC. They will be lepton colliders mainly. But in first approximation, you can think that this is the way in which you want to extend the future. So for tomorrow, what I would like to go into is just to give you a little bit more of an idea of why we are going this way and what is involved, and then to specialize the discussion to get into the core of the discussion and really start looking into what are the building blocks and what does it take to describe collider events, and so to then calculate theoretical prediction that can compare to experimental measurements. Okay.
Thank you, Laura. And questions for Laura? Yes.
Thank you for the amazing talk. And I was wondering, you said that it is hard to get the quartic coupling of the Higgs. Is it because we have like very little number of events?
Yeah.
Or
As
okay.
many statistics, yeah.
Oh, okay. And also I was...
because the rates are also smaller, right? Yeah.
Okay. And I was also wondering, like how technically, for example, the LHC measures the electric couplings, for example. How do they technically do that? Like I see how they get the mass of a particle, but how
Yes.
does they get the coupling?
So like the coupling of the W and the Z, or the coupling of the electroweak, the coupling between quarks and Ws, quarks and Zs, the electroweak part, through
the
different
W.
processes, right? So you go from all kind of processes that have been used at previous colliders as well, like starting also from, I don't know, even things as simple Drell-Young production, that is 2 to 1 QQ bar to Z or W to leptons. That's one, just to set the most basic of them all, right? Through dye boson productions and up to production of Ws and Zs with different quarks, with charm, with bottom, with top, and etc.
Oh, sorry. I mean, like, how do they like technically like
Oh, so
when the
how do they-
machine like get the coupling? I
so-
always thought about that, but I have no idea how they get
Right,
the
I see.
coupling.
So just through the measurement of cross-section and differential cross-section. So the basic building blocks are really cross-sections, so number of events, so how many events of a given kind you produce, right? And then depending on what you're after, of course, it's not just that. I mean, when you have differential distribution, you can have different kinds of, you can build, depending on which properties you're after, you can build different combination of these productions. So sometimes if you look at lap measurement, for instance, there is a measurement of asymmetries between production in the forward or in the backward directions, different kinds of combination of cross-sections, basically,
Oh,
right?
I see. I see. Thank you.
Yes.
Yeah, thank you for the lecture one more time. But I was wondering about that the shape of this GM diagram. I imagine this shape is like, oh, the LHC probed this area and probably excluded this area because it couldn't find it. But I mean, my head, I think that, for example, when it probes like, oh, the new physics can have at least let's probe at least new physics which couples that strongly to the standard model. Like if it probes a certain level, doesn't it already probe everything above? Is the level at which the LHC is probing bounded above as well?
Well, typically, the couplings and the masses are combined. They're correlated, right? So what you can probe, meaning that the fact that there is an area in here is just because cross-sections are functions of both, right? So typically, a collider can probe a certain region because with the statistics that it has and the kind of measurement that it has and the values that it finds for a given cross-section, maybe it's proportional to, if it's a certain value of the coupling, it's a correlated value of the mass. So what you can probe is really what you can either exclude or confirm, but it doesn't go beyond that region, right?
Okay, because in my mind, if you increase the coupling, and you fix the max, for me the cross section would only grow. But is it more complex than that?
No, it's just that.
So
Right?
how come it's bounded above? I mean, the LHC, if the cross section is always increasing, then the LHC could reach that.
So you're saying why for a certain value of the mass?
No, for a certain value above, for a certain level of G above,
these couplings.
Yeah,
above here.
it should be probing that area too.
That it should be excluded. I guess it depends a lot on the kind of relations you have among the two, right? In general, is a correlated relation among the two, so it's not just an entire exclusion.
Okay.
Thank you for the lecture. I have two questions. First of all, when you're talking about the energy of this center of mass, are you already excluding the energy that you lost? Are you already excluding the energy that you lost in circular colliders
No,
in kind of
no.
lab? Okay, you are not excluding.
So that is the energy that you can have in the center of mass.
Ah, okay,
right?
nice. Okay.
That-
And second of all,
So that is taken into account. So if you wanted that energy in the center of mass, you have
I
to
need to
take
put
into
more
account.
energy.
Yes.
okay,
So I
great.
don't know if that's what you mean by included. So that is what you really have in the center of mass.
Mm-hmm.
So you have to make sure that you have that in the center of mass, taking into account that you're losing some.
Okay, I see. And the reason why we want to construct the FCC from Grosjean is because it's larger. I can accelerate the particles more, and I will I will lose less energy because the.
Because it's R. That is the R that goes into the formula.
Okay, nice.
Yeah.
And when we think about the precision, okay, I will find new discrepancies, the difference from the couplings, right? From what I expect from the standard model in the precision. I mean, we can find that, right? I mean, I'm going to precision, and I will measure the couplings with precision. And I will find difference between the things that I expect and what I found.
Yes.
But this doesn't tell us what is the true theory about
No.
the nature.
No.
So it's kind of, okay, I will have something, but I don't know what it is.
No, it's that you have to have more than one thing. And that is also part of the discussion that colliders can have more than one thing. So you can measure more than one thing, right?
I see.
And then a theory has to explain them all,
Mm-hmm.
right? So that is a different story. So the first step is just to find the deviations, and then to have a hypothesis that explain that deviation, and then to have more than one thing to test that hypothesis against everything else that you have precisely measured and compared to theory,
Mm-hmm.
and see if everything else is happy, right? So if you have one deviation, it's probably, I don't know, it's hard to tell what is more difficult or not, but in any case, you have to look at the spectrum of deviations that you have from the standard model. Can be one, can be two, can be more. And you can have different approaches in how to interpret them. So you can have an approach that is, I pick a model that is probably, I know that is likely to explain that deviation, and I make sure that everything else that I measure is consistent with that model. So you do a fit of that model as you do fits of the standard model, right? Or you can take a more general approach and say, I don't want to pick a specific model. I want just to maybe study the problem from the point of view of which kind of effective interactions I can extend the Lagrangian of the standard model with in such a way that I've included, according to certain symmetry principles or any other principle that you want your effective field theory to be informed by, kinds of new physics that then are described by these effective interactions. And then I go and do exactly the same fit. So I take the Lagrangian of the standard model extended by effective interactions, and I go and see if that explains the deviations that I see, and everything else that on the other hand is consistent with the standard model. So you do a fit of this experimental measurement and theoretical predictions that you have in terms of specific models or generic parametrizations, and then try to deduce from there which kind of new physics can explain the anomalies that you see.
Okay, great. Do I have time for one more question? Yeah. If you have money to construct just one kind of collider, which one would be, a linear one or a circular one?
It's a difficult...
yeah, it doesn't matter about Grosjean. Yeah, X like he's not here.
So you're talking, so linear or circular means E plus E minus collider.
You can choose.
No, because if it's a PP collider, it's just a circular collider.
Can
if it's
be.
a muon collider, it's a circular collider. If it's a linear or circular, this sounds to me like E plus E minus, right? So, well, they have they have very similar characteristics and some differences. I would be happy with either one of them, honestly. I would be happy with either one of them.
Give me the highest energy.
Right. So, or I mean, the precision is very similar. Of course, I think that so much else comes into the decision on these machines that both of them can do very good physics. One has to look at a bigger picture and see how do they fit in the big picture of what we want for the future of the field, even beyond them, right? And then there are other considerations that come into play that can be important. But if they were just the last word or the last machine that we're going to get from here to infinity, either one would be fine. So with a circular machine is probably going to have a higher luminosity and to have a more precision than the linear machine. But the linear machine is upgradable in energy, so the upgradability of energy allows us to go up to any plus and minus machine and that maybe can do very good top physics, for instance, that the circular machine cannot do. So there are pros and cons. It's really difficult to do. We cannot have both, right, most likely. So we would have to go with one. And I think both of them have very good pros, right? So I think we'll be very happy if we can get one of them.
Okay, thank you.
Well, there are huge discussions about this, of course. And maybe it's a good topic for the discussion session tomorrow.
You mentioned muon collider, and I was just thinking muon is an unstable particle, so it must be very hard to do a collider. When do
Sure.
we expect it to have? Is there like a...
As you may imagine, that was the first question in the mind of people that thought of a muon collider. The muon collider have a limited lifetime. And so you have to be able to produce a beam of muons during that time scale, before they decay. And that is a problem. That is, of course, a technical problem that is related also to what goes under the... You have to be able to... Producing a beam means also that you produce a very orderly collection of particles. That is your beam. So all these particles, they have very well-defined momentum and energy. They all go together very orderly in bunches in the beam. And you have these very active guys that are the muons that they want to decay, right? And they have a spread of momenta, and you don't have much time to get them in order to collide, right? This is the famous problem of cooling also of the muon.
So is there
the
like,
muon
when do
beam.
we expect it to have it working?
Yes, yes. Well, I mean, I'm not saying it's trivial, but it has been studied. It is currently under very, very close examination and study, and we expect probably more technical developments, for sure, more technical developments. But it has been, if you want, we have a proof of concept that this can be done, right?
Okay.
Yeah, just an observation. You know about the G-2 of the muon experiment? So that's what they do. They have muons circulating, and of course they decay, but it's delayed by time dilation. So there is a proof of concept that at least you can have muons in a circular accelerator. So, yes, of course, this is very far from trivial to have a muon collider. Yeah, and just one more comment, if I may. So your question about the coupling constant, if that's an upper bound, you can ask the same question about the mass, right? And if you look at the plots that Laura showed, there are several bounds on masses of particles, of new physics candidates, and you can see that some of them really. So in that case of the masses, it's a lower bound. So it has to be larger. You exclude things that are lighter. So the mass has to be larger than something, and those are the exclusion bounds. So in terms of the mass, it would exclude, all the way to some region here. But if you look at the plot, there are things that are not excluded, even at the low mass. So this is something we could discuss also in the discussion session, because I think this is interesting too. But so your question goes in both ways, right? The coupling and the mass.
Yeah, like the part about the mass, I had already thought a little bit about it. Maybe it's related to a lot of the background, because when you go to lower masses, there will be a lot of background which you won't be or have any chance to exclude. So I'd imagine like there would be a lower bound, but for the upper bound, I just had no idea whether there was or not.
Yeah, we can discuss more tomorrow. So tomorrow the discussion session will be switched, so it'll be the last one. So any further questions? So I don't see any hands up, so let's thank Laura again for this very nice lecture. So get some rest, I suppose. Homework, yes, there's homework. Yes, you ask homework, you have homework. So see you guys tomorrow, okay?